All right. For those listening, I'm David, and for the rest of you, I'm David as well. Got this first of several in this series on the fundamentals of maths, and I've called it fundamentals and not basics, because everyone thinks when you say basic that it means easy, but basic is the hardest thing. Okay, the hardest things are the basic things, because there's nothing below them to build on top of. And so that's why I'm doing this, so that people can have something that they can look at in the future, and that you guys can have something now to maybe learn a few things that you didn't know about these things, find a different way of having it explained to you that you might not have seen before, and hopefully just get something out of it that means that you can feel good about those fundamentals and move on to do bigger and better things. So that's the idea. So this first one today is about decimals and fractions and scientific notation and rounding. And I'm going to start off with decimals. Okay, and to do that I'm just going to need a volunteer. Someone going to volunteer for me? Yep. You come down and just lie on the floor over here. Sure. Just about here. Lie straight like that on the floor. Yes, yeah, don't fall over. So if I wanted to measure this man, thank you very much, in terms of my feet, it would be 1, 2, 3, 4, 5, 6, 6 and almost 7, but not quite. It's 6 and a bit. Right, it's a big bit, but 6 and a bit. Thank you very much. That's it. So the whole point of decimals and fractions is to deal with the and a bit. Okay, to tell you how big the and a bit part is. Now obviously it'd be way better to use a ruler or a tape measure or something. And a tape measure and a ruler, just like this one, has markings on it to tell you the and a bit. Okay, so I can measure in whole centimetres, and then there's pieces, and I can say, well, it's however many parts of a centimetre. That's the whole idea of what decimals and fractions are for. Hopefully you've been taught that before, but I find it useful to not think about fractions as pieces of a whole, but think about them as the and a bit, because it helps with all the rest of science, basically. So, I'm going to go back to my screen. And talk about decimals. Okay, so we can arrange numbers on a line just like with our ruler. I've marked a number with this arrow which is somewhere between 23 and 24. It's 23 and a bit. I mean, it's a big bit. It's closer to 24 than it is to 23, but it's 23 and a bit. And what we're going to do is we're going to zoom in and figure out a more accurate size for what this and a bit is. So it's somewhere between 23 and 24, and we're going to cut that into 10 pieces. And then those markings are 23.1, 23.2, 23.3, 23.4, 23.5, 23.6, 23.7, 23.8, 23.9. Technically 23 is 23.0. So that's telling you how many of these pieces of size a tenth there are between 23 and 24. And my arrow is pointing just a bit beyond 23.6. So it's 23.6 and a bit. And I want to specify how big that bit is, so I'll zoom in again. 23.6 and a bit. I'll zoom in again, and I'll break this into 10 pieces, and that's 23.61 and 23.62, 23.63. That next decimal place is telling me how big the next and a bit is. Okay, and it's 10 times smaller than the previous one. And you can see it's just a bit past 23.61, so it's 23.61 and a bit. And if I zoom in a bit further, now I've got 23.611, 23.612, 23.613. That third decimal place is telling me what the next and a bit is. And I can see that my arrow's not even past the 23.611. So it's actually 23.610 something. I've got 0 of these 10 pieces, and then there's an extra little tiny bit on the end. And then I'll zoom in again and cut that into 10 pieces, and it's actually 23.6101, 23.6102, and it's somewhere between 23.6102 and 23.6103. So it's 23.6102 and a bit. Okay, and if my Prezi was able to zoom in any further, we would be able to see what the next bit is and the next bit is. Okay? But if we zoom all the way out, it's a number between 23 and 24. It's 23.6102, but at this scale I can't even see most of that. Okay? But that's being extremely precise as to what this number is. But theoretically, it should be possible to get any number and for a measurement or a location on that line to be anywhere. Okay? To be as specific as we like. So that's what decimals are for. Each decimal place records a tinier and a bit beyond where we were so far. So that's the idea. Hopefully you're familiar with that, but that's the idea behind it. And the idea behind rounding is to literally look at that picture and figure out which of the two ends it's closest to at a certain scale. So at the moment, if I wanted to round it off to the nearest whole number, if I look at that picture, it's closer to 24 than it is to 23. So when I round it off to the nearest whole number, it will be 24 because it's closer to 24. And if I go back to the beginning, just a second. If I wanted to round it up to the nearest one decimal place, I look at this, and it's closer to 23.61 than it is to 23.62, so it rounds off to 23.61. You don't actually have to look at the numbers sorry, it's closer, let me just go out a bit. It's closer to 23.6 than it is to 23.7. And the numbers that are there tell you how close it is. 23.61, because it's 1, it's only one of those markers into the space between 23 and 23.6 and 23.7. So the fact that this is a 1 tells me I'm less than halfway, so I have to round down to 23.6. And if I did go in the next one, just come out just a little. No, I did that. Here again, I can look at it and it's closer to 23.6102 than it is to 23.6103, so that's what it's rounding out down to. I'm going to just draw on the paper. It's literally how close is it, and what the next digit is tells you how far it is in the space between that and the next number. So that's my thing with rounding. And I'll go to the document camera now. I am just going to write just a couple of words to talk about what I just said so that it's written down somewhere so that I can put this on, scan this and put it on the website. So, each decimal place records a smaller and a bit. That's the idea behind it. And so if I'm here between 23.6 and 23. I'm just making it up. I'm here between 23.6 and 23.7, then I can cut this into 10 pieces. And this one here would be 23.64 because it's 4 of those pieces between 23.6 and 23.7. So that's the idea of what decimals are for. And rounding off is done by looking at the next decimal place. So this is the mechanics of rounding. Look at the next decimal place after the one that you want. And if it's 0, 1, 2, 3, or 4, then you round down, which means you leave the decimal place as it is. And if it's 5, 6, 7, 8, or 9, then you round up. And I'll show you what it means to round up. And that's literally because if it's 5, 6, 7, 8, or 9, it's more than halfway. Okay? So the idea here it's less than halfway to the next mark on our ruler, and this is more than halfway to the next mark. And that's why we round up or down, because we're trying to see, well, what's the nearest number in a literal sense? I draw it on the piece of paper and which is the nearest number. So if I was going to round off to 2 decimal places, then I would get, well, let's see, 3.6. I'll just do that one softly because I might have to rub it out. 3.60, that's my 2 decimal places, that's the decimal point, and these are the places after it. I look at the next number, it's a 1, which means I round down, so I leave it as a 0. And that's the best chance I have. So if I have 8.1058 to 3 decimal places, that's the number 1, 2, 3 decimal places. I look at this number and it's more than 5, well, it's 5 or more, and so I round up. So I'm going to get 106. And the picture that goes with it is that here's 8.105, here's 8.106, and 8.1058 is there. That next decimal place tells me how many of the steps I have between here and here, so it's closer to 8.106. So there is just one last thing, which is a special case that I need to mention. Okay, so I'm going to do that to 3 decimal places, to 2. Let's have a look. 1, 2. So I look at the next number, and it's a 9, so that means I'm going to have to round this up. So 9 would go up to 10, but there isn't a 10, so I'm going to have to round the next one up as well. So it's almost as if you've got 89 and it's having to go up to 90. So just the rule is that if you have to round a 9 up, then it causes the next one to go up and the next one to go up and the next one to go up. So like that. And the reason is because 2.89, the next number after that is 2.90. Okay, 89 is already 1 step away from 2.9. So if we think about 2.8 and 2.9, 2.89 is already 1 step away from 2.9. So if you think about it, this is 2.80, this is 2.90, and this is 2.89 there. And we're actually here, 2.8995. So the nearest number with 2 decimal places that I'm closest to is that one there. So that's the picture that goes with that sort of rounding. So that is rounding. But there is more to rounding because scientists are all funny about having this significant figures thing. So I should mention that too. I will talk about doing operations on decimals, like calculations. If I don't get to it, I'll keep going next week on calculations because that's what it's also about. So, that's decimals, that's rounding off. The next stage is to try and talk about what happens if your number is really, really, really small. What if I had a number like this? So this is scientific notation. What if I had a number that was really, really, really small? So it's 0.001. 0.00005. So in my diagram that I had there, I'd be, here's 0 and here's 1, because it's 0 point something, it's between 0 and the next whole number. And then 0.0, that would mean that I cut this into 10 pieces. Whoops, that would be more than 10. And 0.0 means that I'm not even to the first mark, because this is 0.1. And then I'll cut this into 10 pieces. And 0.0 means I'm not even to the first mark of that either, so it's somewhere in here. 0, 0, 0.001. And then I keep doing that, and it keeps getting smaller and smaller and smaller until it turns out that I just have this number like way close to that. It's really close to 0. The problem is that in science, sometimes really close to 0 is really important, because everything that we're measuring is in like nanometers or something. It's in this really tiny measurements. And so we're not just going to round that off to give 0, we have to maintain the fact that it's not quite 0. So we have to have a way of representing this number that doesn't require us to write all those 0.00005s. And that's what scientific notation is for. It's giving you how big the number is relative to the numbers nearby, and how big it is relative to 0. Well, relative to 1, actually. So we're saying this number is way, way smaller than 1. That is really bad lighting. I'm sorry, I don't know if I can do anything. Oh, sorry. Don't know if I can do anything about that. Okay. It's way, way smaller than 1, because 1 is my standard of how I'm going to measure these things. So, this is how it's done. The number 5 is bigger than 1. And what I'm going to do is I'm going to find the first number that's not a 0 and say, look, it's 5 of something. Okay, we've got none of these tiny pieces, and none of these even tinier pieces, and none of these even tinier pieces, and none of these really, really tiny pieces, and 5 of these very, very, very small pieces. And so that's what we're going to do. We're going to find the first number that's not a 0 and say, we've got 5 of these really small pieces. 5 of these really tiny pieces. And then we have a number here to tell us exactly how big those pieces are. And those pieces are a tenth, a hundredth, a thousandth, a 10,000th, and a millionth. Okay, they're very tiny pieces. So it's almost like we're saying 5 times a millionth. Okay, that's what we're doing here. And what we have is a number that describes how big that is, that describes how many times we had to divide into 10 our number line in order to get to that spot. So what we're going to do is we're going to say, right, to get a millionth, we had to start with 1, we had to divide it by 10, 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 we had to divide it by 10. We had to divide by 10, sorry, 1, 2, 3, 4, it's not a millionth. I can fix that. If only we could do that in our exam. I had to divide it by 10 6 times to get to a millionth. And so we have a way of recording that. We're going to write it like this. Okay, so the 10 is referring to what we divided by. The minus is saying that we divided, and the 6 tells me how many times I divided by 10. Okay, so this 10 to the minus 6 is representing the size of the slice of my number line that 5 represents. It's 5 of those really tiny slices, which are the 6th step down. I had to zoom in 6 times to get to there. That's the idea behind it. Okay, so this is, they're cut into 10 pieces. This minus means that I'm actually dividing, and this 6 is 6 times. Right, that's scientific notation. And the way to do it is to count how many places it is from where the decimal point would be if you wrote it as a plain number to where it is now. So I'm going to draw the picture again. Okay, if this really was the number 5, the decimal point would be here. I'm going to change colours so that when we do it later it will be more obvious. If this really was a 5, the decimal point would be here, because it always goes after the whole number, right? And in order to produce the decimal point that I really have, it had to go 1, 2, 3, 4, 5, 6 spaces in order to produce the number that I really have. And to the left is minus, and to the right is plus. So I had to go back 6 steps. That's what I had to do in order to produce this. And so therefore it's 5 times 10 to the minus 6. Okay? To get from 5 to the number we really have, I had to move my decimal point back 6 steps, so it's minus 6, because that's what back means. That's scientific notation for really small numbers. Okay? Do need to show you a couple more things for the small numbers while I'm at it. Just give me another example. Okay? So that's stupidly accurate, but the idea is that this number, I find the first number from the left that's not a 0, and it's here. And so it's really 3. So I write it there, and I put the decimal place there after the first number. And I compare the number I have to the number that the number I just wrote to the number I really have. And look at this, it's my decimal place is here, but to move it back to what we had originally, it's 1 step to move it back to where it was before. And so it's actually times 10 to the minus 1, because it's back 1 step. You may notice something else at this stage. If you count the number of zeros, including the one before the decimal place, it'll also be the right answer. This one had 1 0 before I got to the 3, which is minus 1. This one had 6 zeros, 1, 2, 3, 4, 5, 6, before I got to the 3, so it's 6. So instead of moving the decimal place, you can imagine counting how many zeros there are instead. That's what I actually do. I count the zeros, because I find that the moving requires me to draw little arrows on it and everything looks messy. So, but there's nothing wrong with drawing arrows on it. Okay, let me just do one the other way around. (2.01 times 10 to the minus 4). That's telling me that I have 201, and the real location of where the decimal place ought to be is really here, 1, 2, 3, 4 steps back. So it's actually 0.000201. And let's just check 4 zeros, including that one, before we get to the 2. We're all good. Now, in practice, you don't actually have to do all that much converting between scientific notation and ordinary notation. That's just so that we can get a handle on how big these numbers are. 10 to the minus 4 is really small because there's a lot of zeros before we get to any actual decimal places. 10 to the minus 1 is really just point something. Your calculator will automatically do 10 to the minus something after it runs out of zeros on the screen. So if you have a calculator and you have 0.000000, about 15 of them, once it runs out of space to put the zeros, it'll automatically write it in scientific notation. And you should know what that looks like in a calculator or in Microsoft Excel. In a calculator, it will often write it as that, with a little capital E. That's what it will do in Microsoft Excel as well. Some calculators will actually type a little times 10 to the power of, but that's what it means. And if you want to type this number into a calculator, you don't type 2.01 times 10 to the power of minus 4. You actually, there's a button explicitly for it on a calculator. Okay, that's what it looks like in the calculator. That's what the screen will say. Typing in a calculator you will type 2.01 and then you'll press the EXP button. That EXP stands for exponent, which is the number on the 10. And then you'll type minus. Some calculators you can type the ordinary minus, and some calculators you have to put the minus that's in brackets somewhere. So some calculators you can put the ordinary minus, some calculators you have to find the minus that has brackets around it or it won't work. Okay, and that is how you get the calculator, enter that number directly into a calculator. Depending on how your calculator is set up, it might automatically convert it back to ordinary decimal notation. Otherwise, it might leave it that way. You can actually change the settings in your calculator to have things always in scientific notation, or to have it always as decimals unless it's too small. And that's something that if you can't figure it out, I'm sure that someone can help you. Maths Learning Centre stuff pretty clever, even if they've never used a calculator before. So yes, I have gotten it stuck on scientific notation before and really hated it because I can't tell how big the number is without all those zeros. Okay, and I should say that you do not actually need to put brackets around it in order to get it to work properly inside the calculator. The calculator sees all of this as a big blob and it's just one number. So you can just go like 2.1 e minus 3 times 8.4 e minus 2, and it will work perfectly well without brackets. However, I'm always funny about that. I do at least like to put brackets here because I feel worse, but I don't like it. But you don't technically need brackets in order for it to work because the calculator sees all of this here. The calculator sees all of that as a single number and sees all of that as a single number, and it will work perfectly fine. Right. That's the numbers themselves. But I have missed something important now. What about really, really big numbers? Okay, so for really, really big numbers, that's okay because we can write them in scientific notation as well. We just do 10 to the plus because that tells us how many times we had to multiply by 10 to get where we wanted to go. I'm just going to go back to my original example. I'll use a different number so it's not confusing. That's 6 million. Okay? And we can describe how big a million is by starting at 1 and seeing how many times we had to multiply by 10 to get there. Okay, each of those 10s adds an extra 0 to the end of my number when I'm writing it. And so there's 6 10s all multiplied together. That's 6 times 10, 6 times. So the fact that it's a plus is telling me that my number is a really big number. And scientific notation works in that direction too. So I can go really insane. So that's a really huge number. It's like 5 billion, no, yes, 5,203,000,000. I can say that this is actually 5.203. So you always find the first number that's not a 0, which in a big number is always the first number. And then you figure out how many places you would have to move that decimal place to get the number that you really have. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Times 10 to the 9. Now counting the zeros doesn't help here. I could write it as 5203 times 10 to the 6. That'd be great. But scientific notation, this number here has to be between 1 and 10. So you can't write 5,203 times 10 to the 6. You could. That would be perfectly correct. It would not be mathematically wrong. It would be true. It just wouldn't be scientific notation. Okay. Right. Now, I'm going to move on from that and just for a moment talk about significant figures. Significant figures is how scientists run their rounding thing. So they'll say round it off to 2 significant figures or round it off to 5 significant figures or present your answers with 1 significant figure. Significant figures is specifically referring to how many numbers there are listed in your scientific notation. So that number there is got 4 significant figures. They're the numbers that are listed in my scientific notation. So digits so it's how many digits there are in the scientific notation. What that means is if you want to count how many significant figures are and it's not already in scientific notation, you can always convert it to scientific notation and then you'll know. But it also means that in order to convert to scientific notation, you need to find the first number that's not a 0. Well, that means that if you don't want to convert to scientific notation, just find the first number that's not a 0 and then count all the digits after that, and they're the significant figures. So for example, the third significant figure is the third digit in the scientific notation, which is the third digit from the left that's not a 0. So for example, that number there, 0.000201355. I find the first number that's not a 0, it's that one. 1, 2, that's my third significant figure. So it's not the third digit that's not a 0, it's the third digit that after all the zeros of the first set of zeros have ended. So just a second. Damn. It's the first digit that's not in the leading string of zeros. Here's my leading string of zeros here. You find them, and then once that string stops, that's where the significant figures start. So the second significant figure is that 0 there. But the significant figures isn't really talking about what digits are there, it's just talking what spot they're in. So whatever number was in that second spot, be it a 0 or otherwise, that would be the second significant figure. So rounding off to 2 significant figures would be that. Rounding off to 3 significant figures would be that. 4 significant figures, well, it'll end up being a 4 because the 5 will cause me to round up. Now, I can't tell you about how scientists decide how many significant figures you ought to have, because that has never made any sense to me. I apologise. You need to talk to the people teaching you your science or your health science. They have specific rules on how many significant figures are supposed to be there. I believe in general you're not supposed to have more in your answer than you had in the original, unless you're calculating a standard deviation, and then you're allowed to have more. But I don't quite know the rules. So you need to check with your people who are teaching you what their rules are for rounding off and when to round off. Well, I've got about 15 minutes. So I've talked about the idea of decimals. I will talk about calculations more as the series goes on. I want to talk about the idea of fractions as well. So I'm going to do that too. fractions are in a way like decimals, they're just more general. Okay, so decimals are a way of recording the and a bit, and you always cut the next piece into 10 pieces and count how many of those 10 pieces you have. Fractions are designed to tell you what the and a bit is when you can cut it into any number of pieces you want. Okay, so they record the and a bit by telling you how many out of some number of pieces. So, some education researchers believe that you should teach and a half before actually teaching any other fractions. So we're used to and a half, 3 and a half is telling me there's 3, there's 4, there's 3 and a half. Halfway between 3 and 4. Okay? But, that's my example there. 4 and 2/7, well there's 4 and there's 5, and the and a bit is 2 out of 7 pieces. Okay, I've gone 2 out of a possible 7 pieces, and so that's what 4 and 2/7 means. This is a very specialised way of writing numbers. It does not mean 4 times 2/7, it's literally 4 and a bit, 4 and 2/7. Okay? The number all by itself, which is just, 6/8, that number all by itself, well, I haven't got a whole number, that's just the and a bit, so that means it's somewhere between 0 and 1. Okay? It's just an and a bit. It's not 2 and a bit, 4 and a bit, 3 and a bit, it's just and a bit. And so that means it must be 0 and a bit. So we cut this into 8, and it's 6 out of the 8. That's the idea of fractions. The thing is, and this is what happens in maths, the really basic things, basic meaning fundamental, have multiple ways of looking at them. And the multiple ways of looking at them mean that you have to be able to know which way to look at it at any given moment. And fractions are really very general like that, because it doesn't just mean 6 out of 8 pieces, it also means something else. And this is where the fractions normally leave people behind. So I'm going to try and be really clear about this. 6/8 isn't just 6 out of 8 pieces. It also means the result of taking the number 6 and cutting it into 8 pieces. So it doesn't just mean taking the number 1 and cutting it into 8 pieces and choosing 6 of them, which is what we've got so far. It also means taking the number 6 and cutting it into 8 pieces. So also, it also records the result of a division. There's from 0 to 6. And if I cut that into 8 pieces, like that, this number here, which is 6 divided by 8, is the same as that number there. So what you'll find is if I had previously marked my ruler with the number 1, you will find that the number 1 is actually just here. And it's the same position as you would have if you'd just done 6 out of 8 pieces. That is the magic of fractions, okay? That dividing by, that doing a division, cutting a length of 6 into 8 pieces produces the same result of cutting 1 into 8 pieces and choosing 6 of them. So that's one of the key points about fractions, is that they're proper numbers in their own right. They're not just how many out of how many. It's a single number that records a place on a number line. And the reason why the number line is so useful is because fractions are used for measuring things in science. So if you've got a ruler, you can say, well, where is it on my ruler? Measuring cylinder, where is it on my measuring cylinder? That's what the fractions mean. And because they record the result of a division, we don't have to use whole numbers in our fractions if we don't want to. We can use whatever numbers we want. We can use decimals and whatever, and we can treat them the way that fractions behave. And so that's what I'm going to do next, how do fractions behave. The behavior of fractions. Okay, the first thing about fractions, which is the fundamental piece of information about fractions that is used everywhere in the whole of algebra and science, is that some fractions mean the same number. So the fraction a half, which means, if you like, cut into two pieces and take one of them, or take the number 1 and cut it into 2, is the same as 2/4. Okay, so if I take a length of 4 and cut it, if I take a length of 2 and cut it into 4 pieces, those pieces will be size a half. Or if you think about it, if I have 4 pieces and I take 2 of them, that's the same as taking a half, which is the same as 3/6, which is the same as 4/8, which is the same as many of them as you like. Okay, multiplying or dividing the top and bottom by the same thing produces a number which is the same number. Okay, so mult and by the same thing represents the same number. And the same goes for dividing the top and bottom. Okay, there is no multiplying or dividing. Dividing is just going back the other way. 4/8 is the same as 2/4 because I divided the top and the bottom by 2. And this is a classic way that people over in nursing, for example, the nursing lecturers, get really upset when students can't do that. I think they're being a bit too precious, actually, the lecturers, about that. One of the ways that people behave who are familiar with mathematics and have been for a long, long time is that they'll notice if there's a number that divides into both of them, and they'll just divide it straight away. So when they see I didn't cover those sorts of fractions, but that's okay. When they see 124 over 48, it doesn't matter that the top is bigger than the bottom. Okay, that just means that it's actually more than 1, and I'll talk about that in passing in a second. Doesn't mean the top is bigger than the bottom. What a person who's familiar with fractions will do is say, gosh, both of those are multiples of 4. They're both even numbers, so I must be able to divide them by 2. So if I take this and I divide them both by 4, let's see, 100 divided by 4 would be 25, 24 divided by 4 would be 6, so that's 31, and 48, that's 12. Okay, so I can do that and it comes to the same fraction. It's the same fraction. If I wanted to know what that fraction was as a decimal, I'd ask my calculator. I would literally type in 31 divided by 12 and it would tell me the answer. I can guess though. Let's just think about what this means. I take 31, I divide it into 12 pieces, but I could also, division also means take the number 31 and see how many times 12 fits into it. That works just as well. Division's really flexible. It allows you to do multiple things. And I'm going to talk about that at quite a lot of length next week, about how division is related, different kinds of division are related. But 31 divided by 12 is how many 12s go into 31? Let's see, 12, 24, so 2 and a bit. Okay, this has got to be 2 and a bit, 2 point something. Don't know what that is yet, but at least I can have a guess at how big it is. So let's see, this would be 2 and a bit. How many's left over? 24 we've got 7. Just for a second. We've got 12, we've got 24, we need 31, which means we've got 7 left over. So it's 7/12 left over. See, I was a bit ambitious in trying to do both decimals and fractions today, but it's a good start. Okay, so you don't normally need this bit. This bit's not actually necessary. That's not a 0.12. It's just a 12. You don't normally need this part, but whenever I see a fraction where the top is bigger than the bottom, I like to try and think about, well, it must be a whole number and a bit, so I should be able to figure out how big it is. Okay, so that's the major rule of fractions, and the other rule of fractions is that you're only allowed to add, there are 2 more rules. So adding and multiplying, 3 more rules. If you have to go, that's fine, but I am going to just keep recording. So, adding fractions is actually quite difficult. Unless you've got a calculator, you can just ask what the answer is. Multiplying is the easiest one of these 3 to do. Because fractions are really about dividing, fractions are all about division, and multiplication is really closely related to division. And so it's actually really easy to multiply fractions. And the example goes like this. These are really stupid fractions. No, I don't want a 9. Okay. There is no particular reason why I chose those. They're just random numbers. They're prime numbers, interestingly, but that's just me. Random numbers. When you multiply fractions, you times the tops, you times the bottoms. That's the deal. That's it. Okay? If it doesn't currently have a bottom, that's okay. If it was just a 5, 2/3 times 5, well, that's the same as 5 divided by 1. So I can, if I want to, and then times the tops and times the bottoms. So it's just worth knowing what happens when you times by a whole number. And this is where our last idea of what fractions represent is. Fractions don't just represent what happens when you divide. They don't just represent a certain number of pieces out of a certain number of pieces. They also represent a single number that will change the size of another number. So if I had 2/3, that would change the size of the number 5 if I multiply by it. Doing 2/3 times 5 is the same as going 5 is the size I started with. I'm going to go 2/3 of that, and the answer is 10/3, which is about 3 1/3. So 2/3 of 5 is 3 1/3. So the idea is that if you multiply a fraction by another number, it changes the size of the other number. So a fraction like this, where the bottom is bigger than the top, will make the answer smaller. A fraction where the top is bigger than the bottom will make the answer bigger. And it's just good to know that that's how it works out. Dividing fractions. Two-thirds divided by 5/7. All right, I'm just going to show you something so that you can see why this is so complicated. If I think about my fraction as division, you would not normally write this on the page. So I'm just going to put it in a different colour, just around the side here. 2 divided by 3 divided by the result of going 5 divided by 7. That's what we have. And that's the reason I've written that is to explain why it's so difficult to do this. Because we've got a division inside a bracket and then the whole thing's being divided. Like, what the frell? So what we want to do is we want to have a rule that's going to work for us. And the rule that works for us is, when we see this, so attach that division to the 5/7 and turn it upside down. Dividing by 5/7 is the same as timesing by 7/5. And now we can do it because the rule for timesing is times the tops and times the bottom. What does that even mean, like in terms of the sizes of objects? Well, we could say 2/3 is a size. It's a size of on the number line. 5/7 is a size, and I could be asking how many 5/7 fit into 2/3. Well, that many, 14/15. Not quite a whole 5/7 fits into 2/3. That's one way of thinking about it. But I find that if I keep doing that too much, my brain explodes, so I don't, and I just do the maths. But that's what's going on. I'm saying, well, I've got 5/7, which is just a bit over half. Well, it's actually almost, nearly all the way to a whole to a whole 7/7. And I'm saying how many of them fit into 2/3. So not quite a whole one. So 2/3 must be smaller than 5/7. Just another example. With a whole number, 2/3 divided by 5. We can think of that of taking the size 2/3 on my number line and cutting it into 5 pieces and seeing how big the 5 is. Well, and seeing how big the piece is. So we know the answer has to be smaller than it was before. But we can do the same trick as we used to do and treat that as 5/1 and turn it upside down. Dividing by 5 is the same as doing a 5th. So there's an over 1 here, and then the times dividing by 5/1 becomes timesing by 1/5. And so I get 2 times 1 is 2, 3 times 5 is 15. That's dividing by fractions. Now it seems strange that I would do multiplication and then division and then do addition last, but addition's actually the hardest thing to do with fractions on paper. I mean, if you convert them to decimals and get your calculator to do it, it'll all be fine. But adding fractions is the thing that most people get wrong when they do adding. And I have students who are doing, who are engineering degrees, they did specialist maths at school and they can't add fractions either. So it's really hard to remember. So don't feel embarrassed. I have years of experience helping people learn to do this, so I can't forget because every semester I help people do it. So it's like learning French, you have to keep practicing it or it just leaks out. So I've got adding fractions, so I'll just do an example. Yeah, I'll use the same fractions that I've been using so far. 2/3 and 5/7. I'm just going to draw a quick picture of this so that you can have a feel for what we're really doing here. Might use my blue. There's 0, there's 1. And I'm going to cut this into 3 pieces and take 2 of them, right? That there, that distance there, that's 2/3. Okay, 2/3 is there. It's 2 out of the 3 pieces. And then I'm going to do 5/7, right? So I cut this into 7 pieces. I go 5 out of the 7 pieces. And the idea is I join them together. I do one after the other. 2/3 and 5/7 together is like this and this. That's 2/3 plus 5/7. So wherever that ends up, that's the deal. And that's all well and good, but I need to figure out, I know it's going to be 1 and a bit, but I need to figure out what the and a bit is. And I need to figure out it as a fraction, so I need to know how many pieces to cut it into. And the rule is, you have to make the bottoms the same first. So you must make the bottoms the same. I need to make the bottoms equal, or I'm not going to be able to achieve my addition. Because otherwise I'm not going to be able to tell how many pieces to cut the next bit after 1 into in order to figure out the and a bit. So, the way to make bottoms equal, just a second, there was a rule that we learned first about fractions, which is if we times the top and bottom by the same thing, it means the same number. So I can convert 2/3 into something else with a different bottom, 5/7 into something else with a different bottom, and if I make the bottoms match, then I can add them. So what am I going to need to do to make the bottoms the same? The classic trick is to go, well, if I times the 3 by 7 and the 7 by 3, then they'll match. So what I've done is separately, inside this fraction, I've times the top and bottom by 7. The reason I've done that is because I really want to multiply the bottom by 7, but I have to do them both or it's not going to be the same number. So this 14 out of 21, that's the same as 2/3. And this here, this 15 out of 21, that's the same as 5/7. And now because they're both out of 21, I can just add the tops. 29. So they're the two steps in adding. You have to make the bottom equal, and then you have to add the tops. You do not add the bottoms, you just keep the bottom as it is. Once the bottom is equal, the bottom stays the same for the rest of the calculation. And if I really wanted to, I could look at that and go, well, 29 21sts. Well, I've gone past a full 21st and there's 8 left over. So I've got 1 and a bit, and the bit is 8 21sts. That's adding fractions. If you want to talk more about any of this, both a few of you who are left and anyone who's listening, that's what the Maths Learning Centre is for. Drop in, have a chat about it. The people will be able to make up examples for you to work on, and they can do even more. So I think I've done everything that I promised. I have at least once talked about decimals and fractions and rounding and scientific notation. I will talk more about fractions next week when I start talking about the behaviour of numbers. Thanks very much.
Thank you.
You're welcome.